Today we will be learning about galvanic cells, which fall under the broad topic of electrochemistry, which is defined as the study of interchange of chemical and electrical energy. Galvanic or voltaic cells are batteries which generate useful electrical energy. During this explanation, zinc and copper will serve as our primary example. Now that you have the very basic definitions down, we'll now continue with the drawing of the cell. There are two containers with two different solutions and two different electrodes. Although they are often in separate containers, galvanic cells can also be found in one container that is separated by a porous membrane. However, for this project we will be using the two separate containers as a means of demonstration. The electrodes are the conductors at each end of the cell, but not necessarily a metal. They are sometimes gases and nonmetals. These electrodes are then placed in a solution of its ions, often blank nitrate. For example, a zinc electrode would be placed in a solution of zinc nitrate, which would dissociate into zinc 2+ ions. The anode is the electrode where oxidation occurs. The cathode is the electrode where reduction occurs. A wire connects both half cells and allows for electrons to flow from the anode to the cathode, since the electrons that are lost in an oxidation reaction are gained in the reduction reaction in the corresponding cell. There is also a salt bridge which connects the two solutions. The salt bridge is used to maintain electrical neutrality in the galvanic cell by allowing ions to flow between the two half cells and maintain a balance of charges. It usually contains a neutral salt, such as sodium chloride or potassium nitrate. We will use potassium nitrate as an example. The non-reactant potassium and nitrate ions prevent the buildup of charge as the zinc ions enter the anode solution and the copper 2 ions leave the cathode solution. Such a charge buildup would halt cell operation and therefore render the battery completely useless. In the anode compartment, nitrate ions leave the salt bridge to balance the gain of positive charges as zinc ions enter the solution. Some zinc ions also enter the salt bridge. In the cathode compartment, potassium ions leave the salt bridge and enter the solution to balance the loss of positive charge as copper 2 ions leave the solution. Thus, charge is able to flow continually as the cell operates and maintain electrical neutrality, which allows the continuation of the process. As the reaction proceeds, you should notice a change in mass at both the anode and the cathode. At the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Each atom loses 2 electrons and becomes a zinc ion which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons through the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which then deposits on the bar. Therefore, as the circuit runs, the zinc electron decreases in mass, while the copper electrode increases in mass. All this information may seem a little overwhelming at first, so here are some mnemonics to help you remember some of the basic ideas. An-ox. The anode is where oxidation occurs. Red cat. Reduction occurs at the cathode. Fat cat. In a galvanic cell, electrons flow from the anode to the cathode. The cathode is always positive. These are the most basic ideas, but it always helps to keep things straight. Now let's talk about voltage and calculating cell potentials. Voltage is defined as the electrical potential difference between two electrodes. If you are given the equation of the cell reaction, you can determine which half reaction undergoes oxidation and which undergoes reduction. For example, in the case of zinc and copper, the equation is zinc atoms plus copper 2+ ions yields zinc 2+ ions and copper atoms. Zinc is oxidized because it loses 2 electrons to form zinc 2+ ions, whereas copper 2+ ions are reduced because it gains 2 electrons to form a copper 2 atom. A table of standard reduction potentials is often provided to you. The electrode with the more positive reduction potential is reduced, whereas the electrode with the less positive reduction potential is oxidized. In the case that the table of reduction potential values is provided to you, simply compare zinc and copper reduction potentials. Zinc's reduction potential is negative 0.76 volts, and copper's is 0.34 volts. Therefore, copper is reduced and zinc is oxidized. Now we're going to do a few practice problems just so we can get a feel for how to solve these different equations based on what we're given. So, consider a galvanic cell based on the following reaction. We have aluminum ions plus magnesium, which yields aluminum plus magnesium ions. And so, when you're given this reaction, we're trying to solve for the balanced cell reaction and evaluate the cell potential for the cell. So, if we were to, first off, we want to balance this. So first we need the half reactions for each individual one. So the first one is based off the fact that we have aluminum and aluminum,
so we're going to work
and
one
magnesium
more problem,
and
this one's a bit trickier just
so
because
the
the equation
reduction,
because you go from
you have to figure it out by yourself.
to
Okay, so
charge of 0, which means that
the
it gained
cell
electrons.
voltage for the galvanic cell
So
that
that
would
means that it was
utilize
reduced.
silver metal.
So you have, okay, so we have silver metal plus, and involve iron 2 ion and iron 3 ion. So we have
atom.
And you do the same thing for magnesium,
ion and
except
iron
you go from an atom
3
to
ion.
2 plus,
Draw
which
a
means that it
diagram of the
lost
galvanic
electrons.
cell
So you go
for the reaction and label completely.
magnesium to
Okay, so these
magnesium
are
ions.
the materials that involves, and we need to find out what is reduced, what is oxidized.
And so
you have
we
2
go to
electrons
our
and then 3
handy
electrons.
dandy
So in order to
list
balance
of
it,
cell
we need
potentials,
to put 3 at these
and
coefficients
we
and then
see
2 at these
that
coefficients. So our new
silver
equation is
atom
2 aluminum ions plus
the equation
3
for the
magnesium
oxidation
atoms
of silver
yields
atom is
2,
and it is 0.80 volts.
2 aluminum atoms,
And then you go to the iron 2 or iron 3.
3 magnesium
And then we get this equation.
ions. Oh, sorry. There you go. And so now this is our
reduction
final
potential.
final equation right there.
7.
And the second part of the question wants us to solve for cell
this
potential.
one
And so
wants to
obviously,
be
in order to solve
reduced the
for
most.
cell potential,
Therefore,
we need to first
this is what's going to be reduced,
look
and this
up
is what's going to be
the
oxidized.
cell potentials for
So in
each
order to do this, we
half
want to flip
reaction.
this equation.
So if we look it up,
And you get
we see that for the reduction of aluminum ions,
now that we have these 3 equations, we're
Going
ready
back
to
to
write
this equation.
our final one.
is negative 1.66
Okay.
volts.
So
And then next up, we're trying to find
you have on the
we're trying to
left
find
side
the
of equation, you
magnesium
have
potential.
silver ion plus iron 2 ion.
So
which
this
yields
is the oxidation
silver
equation.
atom.
And so in order to get the oxidation
And
reduction
iron
potential, we need to
3
flip the
ions.
sign. And so originally it was
And then
negative
this equation is already
2.37.
balanced because each one
So we
uses
flip it
just
and it
one
becomes
electron, so you don't have to worry about adding any
2.37
coefficients.
positive.
So
This
that
is negative
is
and then
your
this is
equation.
positive. So all you gotta do is add these 2 up. And our answer is 0.71 volts.
then,
and so that is
if
the
we want to find
cell potential for
the
this
cell
equation right
potential,
here.
we compare our
And
cell
there you go.
potentials, and if you remember, the reduction
Of silver ions, excuse me, 0.08 volts. And then the other one was the other way around. So if we flip it, we go here, it's negative 0.77 volts. So if you calculate cell potential, you just add them up, and you get 0.03 volts. And there you go. That wraps up our little mini unit on galvanic cells and electrochemistry, so you now have a very basic and broad understanding that will serve as an excellent groundwork. So that's all, folks.